The 2026 AP Physics Mechanics exam was known for a particularly hard number one for the FRQ, and particularly part A because it had a complex situation, but more than that, it required a lot more calculus than is typical for the AP Physics C exam. Let's take a look at that, number one. So first, the scenario we have is we have a box that's moving to the right. Within that hollow box, there's a cube that's pressed against the right wall because it's slowing down. So there's a resistive force, it tells us, that's proportional to the velocity. So that resistive force is negative BV, where B is a constant. And we're told there's a few different times. At t equals 0, it's sliding to the right with a velocity v sub 0. Then as we get from 0 to the t crit, the cube is remaining in contact with the wall at the same place. Then once we hit that t critical point, it tells us the box starts falling down. And so the resistive force, the acceleration, it's gone down enough that that friction is no longer strong enough. So part A had three parts. The first part was fairly easy, and it kind of lulled into a sense of false security when you look at the next two parts. But it says determine an expression for the magnitude of the acceleration of the cube specifically. So we're just looking at the cube, and it says express our answers in terms of m, f sub n, and physical constants as appropriate. Well, we can recognize that cube. What are the forces acting on it? Well, since it's slowing down, it's accelerating to the left. That means the box is giving a normal force pushing on the cube to the left. That normal force is creating a resistive force, which is a friction force. Well, we know gravity is pulling it down. So then resisting that is that friction force going up. So then what this asks is, what is the acceleration? Well, we already know the acceleration because of the overall picture is going to be to the left. And the only force working to the left is F sub n. So we know the net force in that direction is F sub n, and it equals mass times acceleration. Now, the mass of that cube is capital M, and then acceleration we'll just call A because that's what we're solving for. So pretty simply here, then the acceleration of the cube is the normal force divided by mass. And that's all we have to do there because it tells us that's what we can keep our answer in terms of. That's the answer to part A, 1. But part 2 is where this gets tricky. Now it tells us to derive an expression for f sub n as a function of t. So we haven't been given anything directly that gives us a function of t, but we're going to get it from t equals 0 until the point where it says before the cube reaches the bottom of the box. In other words, when it comes to rest on the bottom. So we have a few things we can use. We can use m, b, v sub 0, t, and physical constants. And it says begin your derivation with a fundamental physics principle or an equation from the reference information. Well, what we can recognize here is our force. So on the overall system, the only force working to slow this box down is F sub r. So our net force we're looking at is F sub r equals the mass, which the mass of the system is the box, which is m, plus the cube, which is m. So that's 2m and then a. Now this acceleration is going to be the same acceleration as the cube in that direction. So we can recognize that these are going to be the same, but we don't have any time here. So let's simplify this a little. Not simplify, but solve for a. We're going to divide 2m over and also recognize that f sub r is equal to negative bv. So we're going to put negative bv over 2m. Now, how do we get this in terms of t? Well, one thing we can recognize, acceleration is a derivative of velocity in terms of time. So we're going to actually rewrite acceleration and say that acceleration is dv dt equals this negative bv over 2m. So from here, we recognize we have a differential equation we can solve. We want to separate our variables. So we're just going to do that here. We're going to divide v from the right side to the left side and then multiply dt over to the right side. So we have dv over v equals negative b over 2m times dt. Once it's separated like this, we can keep it like this because b and m are both constants, so they can stay there. We're going to integrate, but we have to be deliberate because it's not an indefinite integral. It says we're doing it from t until the point when the box reaches the bottom, so an indeterminate time. So we're starting from time 0 and going to time t. And what is then our bounds here? Well, we have to think of velocity. At time 0, we were told the speed was v sub 0. At time t, we don't know what the velocity is, so we'll call it v of t. We could also just call it v, I'll say v of t here. And then we can integrate. The antiderivative of dv over v is the natural log of b. And we're doing that from v of t to v sub 0. And then over here, it's all constants, so we just add a t to this all. So it'd be t from 0 to t. We can recognize on the right side, plugging in 0 is going to get 0. Plugging in t, obviously, will get t. So it's just going to be that. On the left side, we'd have natural log of v of t minus natural log of v of 0. If we remember our logarithm rules, subtraction we can turn into division. So this is v of t over v sub 0 equals negative b over 2mt. Then the last thing to solve this, we're going to take e to both sides. That'll cancel out the natural log, and then we'll multiply our constant v sub 0 over. We get v of t equals v sub 0 e to the negative b over 2mt. Now, we might think we're done there, but unfortunately, we want to remember we're not finding velocity, we're finding f sub n. F sub n was found way over in this equation up here. F sub n equals m times a, or a equals f sub n over m. So we need to get this in terms of acceleration because this acceleration was the same as the acceleration of the system. To get acceleration, though, we can just take the derivative now in terms of t. So the derivative velocity is acceleration. The derivative of this, e, is itself, but then chain rule, the derivative of negative b over 2mt would be negative b over 2m. So we're going to have negative b, sorry about that, vo over 2m e to the negative b over 2mt. That's our acceleration function. Now we can plug that right back into here. So we can recognize f sub n equals m times a of t. So times negative b v sub 0 over 2m e to the negative b over 2mt. Simplifying that, the m's cancel. Just going to erase that here. And we can see, we can double check here, is our answer matching that we're using all the constants that we need? Well, we can see we have b, v sub 0, t, which we have it as a function of t, and m, and then e is just a number. So all of this is using what we need, and it is what f sub n equals. So that would be the answer to part 2. So really quite a difficult one on the AP test, a bit of a time constraint one there if you were taking that and struggling with it. But that ultimately is the answer there. If there's any questions on that, be sure to leave those in the chat and hit that like button and subscribe. But we're going to look also at part 3 of this. Part 3 was a little easier. It said on the axes shown in figure 2, sketch a graph of the magnitude of the frictional force. Now we can remember the frictional force for the cube was pointing straight up, opposing the force of gravity. So from time equals 0 to time critical, that cube isn't moving. What does that mean? Well, that means the force of friction is perfectly matching the force of gravity. That means mg is the frictional force all the way up to that point. Now, what happens at that point? Well, then the box starts sliding. The moment it starts sliding, we're no longer using our mu sub s. It's not static friction, it becomes kinetic friction. And mu sub k is always smaller than mu sub s, which means immediately we have a drop in the frictional force. And then from there, it's going to be sliding down. The velocity is slowing, which means as the velocity keeps slowing, the acceleration is going down. That friction is getting less and less. So we're going to have a decreasing function that looks something like this. It's concave up like this, decreasing, and eventually it's going to hit 0 because that box is going to hit the bottom. There's not going to be that friction because the whole box is going to have stopped. So if there are any questions, make sure to leave those in the comments. This is one of the hardest AP Physics C questions I've ever seen for the FRQ. It took a lot of calculus, a lot of different work, but it is doable. It is solvable if you know your principles well, you know your calculus. If you enjoyed that, make sure to hit the subscribe. We'll be doing AP Physics content throughout the year, also AP Calculus and other math classes. So